Welcome to another video lecture session on crystallography. In this lecture, we are going to talk about the concepts related to solid structures. In crystallography, when we try to explain what kind of different types of solid is there, then we start with defining the concepts like what is unit cell, what is a basis, lattice, then Bravais lattice, different types of lattice, how do you distinguish between different types of Bravais lattice, etc. In this lecture, we'll cover these 4 different points. Actually, the last point, I'll leave it for you to understand as a homework, but I'll give some hint related to the last point. So let's start with this, that when you see some solid material around you, then you can categorize them, the solids, into 2 different types of solids, broad categories. One is called crystalline solid, another is called amorphous solid. In a crystalline solid, the atoms or the units or the building blocks or the molecules of which the material is made up of, structurally the units of the material, they are arranged in a periodic fashion. And these units, when I say periodic fashion, I mean one unit of a structure gets repeated in different directions periodically, right? And in case of an amorphous solid, then there is no such repetition or periodic arrangement in the material. Rather, the atoms or the molecules of the materials are randomly distributed or arranged throughout the material. So in case of a crystal or a crystalline solid, the points where the atoms or the molecules are placed, they are placed in periodic fashion, right? So those points where they are arranged, they are placed, those points gives you a geometrical structure, and that is called a lattice. So lattice is a mathematical object, and when you put atoms or the particles on the lattice, that gives you a physical structure, a solid, right? So a lattice is made up of some basic units. So in a lattice, you have repetition of something, of a structure, repetition of a unit structure, and that unit structure is called the unit cell of the lattice. And here what we are showing is that, let's say if you have just in one dimension, then let's say imagine a line, and that line starts from here. A line starts from this point, and there is one atom here, and with a distance of certain unit, you are repeating that point. Then these points here, these points are forming you the lattice. What is the unit? Unit is this much. You are basically repeating this distance to generate next point, and so forth. So this would be like your unit cell, right? So when you put atoms at these points, then you form a one-dimensional crystal like this, infinite along this direction or along this direction, in both directions. So if you go in a 2-dimension, then you can extend in one direction, and also you can extend your system in another direction. So for example, in this case, the unit that you repeat is A along horizontal direction, and this vertical direction, the unit that you repeat is B, right? So at any point, and this whole 2D structure is made up of by repeating this A and B. So A is like your unit vector, and B is like another unit vector along this direction. So if you want to put any atom in a particular position, in a particular lattice point, then what you have to do? You have to move some integer numbers along A times. So it's like 1, 2, 3 times along A direction, and then 2 times along B direction, and that's where you go. And that's how any point on this lattice can be identified by a corresponding vector, and this vector would be sum of this U and V, sum of this A and B with this U and V, where U is like U times go along A, V times go along B. right? So in this way, you can identify each and every point in this 2D lattice. Like in one direction, you will only need one, and let's say that's U. So R, any position along this lattice, one-dimensional lattice, would be given by UA. So now you can imagine that if you want to do it in 3D, how many you have to do? How many of such vectors you need? You need 3 vectors. A, B, and C are corresponding. You will need 3 numbers, U, V, and W. So that's a 3-dimensional lattice. And in that 3-dimension, let's say this is your A direction, this is your B direction, and this is your C direction. Then at any point, let's say this. How many times you have to go along A? None. But how many? So 0 along A, 3 along B, and then 2 along C. So in this case, the coordinate of this is 0, 3, 2. So you'll put here 0, 3, 2. That's how you can assign any point on this lattice a vector identified by these three numbers, U, V, and W, right? And these 3 unit vectors would form your unit cell. So you move by A amount in this direction, B amount in this direction, C amount in this direction. And then this cube that you form is called the unit cell, right? So you can move by unit amount in all directions, and then you can reach all of these 8 different points. And again, in this case, the picture is drawn as if this A, B, C are perpendicular to each other, but they may not be. So if you have these angles, alpha, beta, gamma, these 3 different angles to be not 90s, then they will form a non-cuboidal unit cell. So by having 3 different quantities, and these quantities are A, B, C, and I am now saying that they are vectors, right? They are vectors. But a vector has what? A vector has a magnitude and a direction. And these 2 can be captured by 3 different numbers, A, B, C, and alpha, beta, gamma. If I give you A, B, C, the unit, the absolute values of these vectors, magnitudes of these vectors, and the angle between them, alpha, beta, gamma, then you can uniquely identify in which directions these vectors A, B, C are. So these are basically in terms of some scalar numbers through A, B, C, alpha, beta, gamma. These 6 different scalar values would give you would give you uniquely identifiable different unit cells, right? So these unit cells are called Bravais lattice, for which A, B, C, alpha, beta, gamma are different, right? So it has been found that with these 6 different scalar values, 3 are magnitude and 3 are angles, a total of 7 crystal systems can be defined. And then when you choose where to put the atoms, then you can uniquely identify 14 different kinds of lattice unit cells. And those 14 different unit cells are called Bravais lattice, right? So remember very clearly, with this 6 different values, 3 are magnitudes, 3 are angles. Magnitudes of what? Magnitude of these unit vectors. You can identify 7 different crystal structures, okay? But then when you want to put the atoms on these crystal units, unit cells, then you have some more. How many total? 14 different kinds of unit cells. And those unit cells are called Bravais lattice. And let's see what are those. So here, the first three are with A, B, C, all are equal. Let's say A is equal to B is equal to C is equal to 1. And alpha, beta, gamma, all are equal to 90. So when these two conditions are satisfied, then you get one type of crystal systems, and that is called cubic crystal systems, right? We'll come into detail. Then when you have A is equal to B, not is equal to C, but alpha, beta, gamma all are equal to 90, then you get another type of unit cell, and that is called tetragonal unit cell. So how many we have? Cubic unit cell, tetragonal unit cell 2. Third is called orthorhombic. In that case, A, B, C are all unequal. They are not equal to each other anyway, but alpha, beta, gamma are all same, still 90 degrees. In that case, you get orthorhombic. All these are orthorhombic. So third. Fourth is called monoclinic. In this case, A, B, C are not same. Alpha and gamma are same, and that is equal to 90, but beta is not 90. Okay, two of the angles are same and they are 90, but one of them is not, right? So you have, in that case, it's called monoclinic. So 1, 2, 3, 4, 3 more, right? 7 total. Then another is called rhombohedral. In this case, A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to not 90 degree. So there could be anything. So alpha is equal to beta is equal to gamma is equal to maybe 45, 50, 70, 80, 90, not 90, sorry. So in that case, you have a crystal system unit cell which is rhombohedral. Then you have hexagonal. In case of hexagonal, it's A is equal to B is equal to not is equal to C, and then alpha, beta is equal to 90 and gamma is equal to 120. So here this is 90, this is 90, but this angle is 120. In case of triclinic, you have everything different. So you have here 3 different crystal systems, and 1, 2, 3, 4. 4 different crystal systems. So 3 plus 4, 7 different crystal systems. And then now in this cubic crystal system, if I now arrange or put the atoms in different positions, then I get 3 different uniquely identifiable 3 different crystal systems within cubic system, and those are called Bravais lattice. So first, if I put the atoms only at the corners, you get simple cubic Bravais lattice. If I put the atoms not only at the corners but also one more atom at the center of this cubic box, then I get body-centered Bravais lattice. Body-centered cubic Bravais lattice, BCC Bravais lattice. Now I have 8 atoms sitting at the corners, and then 6 more atoms placed at the center of the 6 different faces. So you have face-centered cubic Bravais lattice, FCC Bravais lattice, or simply FCC lattice. So 3 different for cubic, 2 different for tetragonal, 4 different for orthorhombic, 2 different for monoclinic, and then 3 more here. So in total, 14 different Bravais lattice. Here, first you have to remember how many crystal systems you have with these 6 scalar numbers, A, B, C, and alpha, beta, gamma, angles and magnitudes of these unit vectors. You have 7 crystal systems. Then, if you now put atoms on these crystal systems, then you get 14 different 3-dimensional Bravais lattice, right? So these are all called Bravais lattice. Let us take some example of this different materials which come in different which come with different Bravais lattice. So their unit cell. So for example, silicon, aluminum, then silver, then gold, iron, sodium chloride, all are cubic, right? Indium, then indium is tetragonal and so forth. Zinc is hexagonal and so forth. So these are different examples of different having examples of materials having different crystal systems as their building blocks. Now, in this lecture, what are the different types of solids you have? To describe the solid structure or the crystalline structures, you have some terms or some concept that you have to understand. These are called unit cell, basis, lattice, Bravais lattice. How many such Bravais lattice? 14 such Bravais lattice. Now, my question to you is, when I was describing these 14 different Bravais lattice, you would see that there is no FCT Bravais lattice. Okay. My question is, why there is no FCT Bravais lattice? If you draw this FCT Bravais lattice, then you will see that FCT Bravais lattice turns out to be BCT Bravais lattice. Okay, again, what is FCT Bravais lattice? FCT means face-centered tetragonal Bravais lattice. What I'm saying is, so this is your BCT Bravais lattice. So you have a tetragonal system, unit cell is tetragonal, and then you are putting one atom at the center, so you got BCT, body-centered tetragonal Bravais lattice. And I'm saying why there is no FCT, why this is not available. You see here, you have, for the cubic system, you have BCC, so it's like BCT, and then you have FCC. So cubic system FCC, so face-centered atoms are there, but for the tetragonal, there is no such Bravais lattice. Question is, why? Answer to that question is, I am leaving some part unanswered, but one part of that answer is, if you try to draw a FCT, right, with atoms at the centers, not at the body center, at the face centers, not at the body center, then what you will see is that you can see that body-centered tetragonal is actually there in face-centered tetragonal. So in other words, BCT and FCT are equivalent. But then we made the choice, which one to choose. If they are identical, then which one to choose? Generally, there is a rule that you choose those unit cells which has less numbers of atoms in them. Okay, we will tell you how to count how many atoms are there. For example, let's say if we do it here, how many atoms are effectively in this unit cell? In this simple cubic unit cell, there are only one atom in this unit cell. How many atoms are there in this unit cell? There are 2 atoms in this unit cell. Why there are only one unit cell in simple cubic? Because you see, each corners are shared by 8 different unit cells nearby. So this corner contributes only 1/8 to this unit cell. So there are 8 corners. So you have effectively only one atom contributing this simple cubic system. In case of, again, for this body-centered cubic unit cell, we have one atom at the center, so 1. And then 8 different atoms at the corners, each of them contributing 1/8 to this unit cell. So we have one more, so 2. How many are there in this face-centered cubic cell? You have 8 corners, so they contribute only 1. Then at the face, each atom that is placed at the face is shared by 2 different unit cells. One just next to it, So in a real crystal, you will have another unit cell here next to it, right? So this atom is getting shared with this unit cell and with this unit cell. So this atom is contributing only half to this unit cell. And that's why each phase atoms is contributing half. So how many such phase atoms are there? 6 phase atoms are there. So all of them combined is contributing 3 atoms to this unit cell. And thus you have 3 plus 1. 1 is from the 8 corners. So 3 plus 1, 4 unit atoms are. So 4 atoms effectively in the FCC, 2 atoms in BCC, and only 1 atom effectively in the simple cubic Bravais lattice. Similarly here also, 2 atoms, 1 effectively atom, and FCT you will have 4 different atoms, right? So as I was saying that if you draw BCC, which is here, and if you draw FCC, that's part of your homework, you will see that they are equivalent, and then you have to choose which one to choose. And the rule is you choose that Bravais lattice which has less numbers of effective atoms in it. So FCT would have 4, so we don't choose that, right? So that's why you don't have FCT Bravais lattice in this list of 14 different Bravais lattice. With this, we are at the end of this session, and in the next session we'll talk about something called Miller indices and atomic packing fractions. Thank you.